Honors Geometry, Unit 3, Day 2 notes. We're going to start right off with some vocab here for you. The circumcenter of a triangle. Circumcenter is the point where all your perpendicular bisectors, well, if it's a triangle, there are three perpendicular bisectors intersect, or they meet in one point, and that's called your circumcenter. So in this particular picture that we have been given, this diagram, point N is the circumcenter, because it tells us that Kn, Ln, and Mn are all perpendicular bisectors. So if you remember back from the day 1 notes, a perpendicular bisector doesn't have to start at a vertex, okay, which Kn does not, but it is perpendicular to, and it says it's a perpendicular bisector, so that also means that Kg and Kj are congruent segments. Okay? It also tells us that Ln is a perpendicular bisector. I don't know if Hj and Jg were congruent to begin with, so I'm going to put 2 congruent slashes because I don't know if this one and this one are congruent or not. Right? And then finally it says that segment Mn is a perpendicular bisector. All right? So the fact that they have said that these are all perpendicular bisectors tells us that the point where they all meet, where they all intersect, that is our circumcenter. Okay, so now let's take some given information that they have for us here. All right, Ln is 32 units long. This guy right here. They also tell us that GK is 84 units long. And it tells us that Gn, which is this guy, is 130 units long. All right, so just a couple of quick things on perpendicular bisectors. First, the 2 things that you already knew. They are perpendicular to, which means they make a 90-degree angle, and they bisect a side. Okay, each perpendicular bisector is perpendicular to a side, and it bisects that side. The only other thing that I'm going to offer you is this, that if I have a side length, so let me just redraw GJ. There's GJ. Okay. If I draw a perpendicular bisector to it, okay, if that's a perpendicular bisector to the segment GJ, then this is kind of an important, well, definitely for this topic, a very important fact. And that is that any point on the perpendicular bisector is equidistant from the endpoints, point G and point J, which just means that any point on that perpendicular bisector, if I connect that point to both J and G, I would see that those connecting segments would be congruent. So if I have a point here that's on the perpendicular bisector, then if I draw a segment to the endpoints, we're going to have congruent segments, right? So any point on a perpendicular bisector is equidistant from the endpoints of the segment that it bisects. All right, so now let's see, what do they want us to find? We want to find Hn. We want to find Lj. We want to find Gj. Okay, so let's go down in order here. Hn, well, Hn is this fellow right here. All right, now how are we going to find that? Let's look at what they've given us. Okay, let's look at what they've given us and see what different things we can get from that. Right now, I mentioned that on the perpendicular bisector, it is perpendicular to and bisects each side, and every point on it is equidistant from the two endpoints. All right, so we want HN. Is there a segment that they have given us that can lead us to HN? Okay. Well, think about that last property of perpendicular bisectors that I just mentioned. From any point on a perpendicular bisector, you have the same distance to each of the endpoints. So HN is the distance from point N, which is a point that's on all the perpendicular bisectors. Okay, it's our circumcenter. And it goes to one endpoint, H. Well, do we have another segment like that? Yeah, we do. From N to this endpoint G. Wow, look at that. So if NG is 130, NH has to be equidistant. Okay, it's got to be congruent with NG, right? So N is equidistant from H and G, which means that if NG is 130, NH is 130, 130 units. How do I know it was congruent to NG? That's how I know. Okay. All right. The next segment that they want is LJ. Okay. LJ is right here. All right. Couple ways we could do LJ. Right. I think we should use the fact that LJ and LH are congruent. How do I know? Because NL is a perpendicular bisector. It bisects HJ, means it cuts it in half. Okay, so I know that this segment and this segment are congruent. Well, how can I find LH? Well, look at this triangle right here. See that triangle? You've got a triangle that's a right triangle. How do I know it's a right triangle? Because perpendicular bisector. And you have two of the three sides of that triangle. So I have a right triangle with two out of the three sides. I can use the Pythagorean theorem to find the third side. Okay? So if I want to find LH, all right, I'll even keep it as LH when I do the equation. You can use A squared, B squared, C squared, whatever you want there. Just remember, LH is a leg. How do I know it's a leg? Because it's one of the two sides that makes the 90-degree angle. Okay? 130 is the hypotenuse of triangle HLN. So for my Pythagorean theorem, I would write, let's go back to the gray, HL squared, put parentheses around it, plus the other leg squared, 32 squared, equals 130 squared. Okay, now we just have to do a little bit of arithmetic, not a big deal. Okay, 32 squared, 32 times 32 is 1024. Okay, so let's change color just so we have that. 130 squared, 130 times 130 is 169, then 2 zeros, so 16,900. Okay, so if you want to write it all out, HL squared plus 1024 equals 16,900. We subtract 1024 from both sides of the equation. Let me write it. Let's go over here. So then we have HL squared is equal to, let's subtract 1,094 from that. So it'll be 15,000. And then 94 from 900 would be 8. excuse me, 24 from 900 would be 876. And then we are going to take the square root of both sides, and we'll find out that HL is equal to, okay, take square root, and oh yeah, 15,876 actually is a perfect square, which is kind of nice because when you hit the square root button, you get 126 units. So if HL is 126 units long, since NL is a perpendicular bisector, means that L is the midpoint of segment HJ, tells me that this is also 126. So 126 units for LJ. The reason that HL is congruent to it because of bisecting, and then because we got perpendicular, we have a right triangle, and we already had 2 of the 3 sides of the right triangle. Okay, it's kind of nice, it's kind of smooth how it's going along here. GJ. GJ is the last segment that they want. All right, GJ is this long segment. What did they give us that kind of gives us everything we need here? They gave us GK. Okay, so we've used the perpendicular part and the bisector part already. Now the bisector part, we're just going to look at it again here. You know that GK and LK are congruent, so that kind of gives it away. We got 84 units. Okay, all right, so that's the circumcenter. Circumcenter is perpendicular bisectors and where they meet. So please remember perpendicular and bisector, and every point on the perpendicular bisector is equidistant from the 2 endpoints. Okay. Now the second vocabulary term that we're going to be looking at today is called the incenter. Okay. So whereas the circumcenter involved perpendicular bisectors, the incenter involves angle bisectors. Okay, so we know that angle bisectors bisect angles. So whatever vertex the angle bisector came from, it cuts that angle in half. Okay, the angle at that vertex. So where the 3 angle bisectors meet, that point is called the incenter. Okay, so with that in mind, let's look at this diagram here. So we know that they said angle bisectors are AV and BV and CV. Those are all angle bisectors. So AV cuts what used to be angle A in 2 equal halves. BV cuts what used to be angle B into 2 equal halves. And then CV cuts what used to be angle C into 2 equal halves. Okay, so that's given to you. So you're going to use that given information along with this given information. It says given the length of TV is 18 units. So this guy right here is 18 units. Okay. The length of CV, let's pick a different color. The length of CV is 27 units. And the length of, the measure of angle TCU. So T, then C, then U. So this angle right here, okay? This angle right here. Oh, let's do it like this. TCU. So this angle, the big green angle, it's 22 degrees. And then they give us the measure of angle SAV. SAV, S-A-V. That angle right there. So the gray angle says it's 32 degrees. Okay, so that's our given information. That's a lot of stuff, actually. So I'm hoping that these will be pretty straightforward and pretty quick. I bet they will be, right? So now it says they want the measure of angle SAU. They want the measure of angle SBV. And they want the length of segment SB. All right, let's get after it. SAU. 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 So this angle right here. Okay. I hope you can see that SAU is made of the two angles that were created by the angle bisector. And if one of them is 32, the other one is 32. So 32 plus 32 gives us 64 degrees. And that's a 4, I promise. Okay. The measure of angle SBV. SBV. So SBV. This guy right here. SBV, we want him. So keep the outline there. That's the one we want. Well, how can we find this one? Well, I can think of a few ways here. If you are looking at, well, we could look at the big triangle. Okay? We could look at the giant triangle here, this big guy. And you could say, I should know all of these angles. Like, for example, they gave us that this angle here is 22. Okay? Actually, let's do this. Let's copy this without all of the angle bisectors in. Triangle ABC, before all the stuff was written into it. All right. And we have that angle A is how big? Well, we got 32 and 32. That's 64 degrees. Okay, angle C, they gave it to us. They've already given this. This is angle TCU. That's 22 degrees. Okay, now we should know angle B. We should be able to find angle B. And I know that you all know how to do this. You would take 180 and you would subtract 64 and 22. So you're subtracting 86. And you would get 94 degrees. So if angle B is 94 degrees, then the angle that we want, this angle right here, because of the fact we have an angle bisector, we know that angle SBV is 1/2 of that 94 degree angle. Okay, so half of 94 is 47. So I know this is 47. And this other guy here is 47 degrees if they ever ask us for that. They're not going to, but they did. We should know it. Okay. So the angle bisector gives us all of the angles, which is nice. Okay, now we want to find the length of segment SV. Okay. So how do we find SV? SV is here. SV is a segment that is perpendicular to AB, because there's a right angle, and it starts at the in-center V. Okay. So we need one more piece of information to do this guy. So remember with the circumcenters, the piece of information I gave you was that every point on the perpendicular bisector is equidistant from the two endpoints of the segment that is bisected. Okay, well, an in-center is equidistant from all three sides. Okay, now How do you find the distance from a side or a segment? Well, you drop a perpendicular to it and you measure it. Okay? Like if I'm holding this pen above the floor and I say, how high off the floor is it? What's the distance from the pen to the floor? You measure straight down, okay? Because you want your pen to the floor to make a 90-degree angle. And that is the shortest distance from the pen to the floor. So from point V to, let's say, segment AB, from V to that side, the distance would be this segment SV. How do I know? Because it's perpendicular. Perpendicular distance is the quickest distance because it's a straight line. It's not diagonal, all right? So that tells me that in this particular picture that VT is here and VU is here and VS which is here. Okay. Those are all lengths of segments created by the incenter and the perpendicular endpoint to each of the sides. So those measures are all equal. Okay, well, we already know VT or TV, okay? This is 18. So this is 18. And this is 18. So that's 18. 27 was just there so that they could test to see that you knew what you were doing, okay? The 27, you know, if you wanted to do like right triangles, then you could find some other segments, but to find SV, you just needed to know that SV and TV and UV are all congruent because V is the incenter of that triangle. Okay, all right, let's go. Next question. This is the last vocab word for the intersection of special segments. This is the centroid. The centroid is created when you draw the three medians and the medians intersect at one point. We call it a centroid. Okay, that's kind of cute, huh? All right, so for the centroid, let's look at what we're trying to find here. We are trying to find the length of JN. We want the length of QM and the length of QP. All right, let's see what we are given. What are we given? We were given that JN, KP, and LM are medians. That's very valuable information because medians start at a vertex, and then when they hit the opposite side, they hit it at the midpoint, which means that it bisects the segment. Okay, so JP and LP are congruent, JM and KM are congruent, and KN and LN are congruent. Okay, that's pretty nice. All right, so KP, let's get a different color here. KP is 36 units long. KP is this big guy right here. So the blue one is 36 units long. JQ is this guy. He's 22 units long. And LQ is this guy right here. LQ is 16 units long. Okay, so let's see what we have at this point. All right, we need to learn the Centroid Theorem. Ooh, sounds fun. It is kind of fun, actually. All right, so we looked at the circumcenter being equidistant from all of the endpoints. We looked at the in-center being equidistant from the perpendicular points of the sides. And now the centroid. Okay, check out the centroid's story. If you start at the vertex of a triangle and you're going toward the midpoint of the opposite side, which is what the medians do, okay? So if, for example, we start at K and we're going towards the midpoint of the opposite side, P, okay? As we're traveling along, the centroid is 2/3 of the way there. So the centroid is 2/3 the distance of the 2/3 away from the vertex, okay, versus the entire median. So we could say that if we're looking at the one we just drew, KQ is 2/3 of KP. And let's look at the other ones. JQ is 2/3 the length of JN. Okay. And then finally, if we look at the last median, which is LM, okay, from the vertex to the centroid, that would be segment LQ. Okay. Let's keep it orange. LQ would be 2/3 the entire median LM. Okay. Now also think about this. If the larger portion of the median is 2/3, then the other portion is 1/3. Okay. And 2/3 is double 1/3. Okay. That's all the information we need. We got plenty of stuff. All right. Let's go ahead and let's answer these questions. So JN, start with JN. So from J to N, so that's an entire median, and they've given us JQ. Well, we already know that JQ is 2/3 the length of JN, and they gave us JQ. So let's substitute for JQ the 22. Okay, so we know that 22 equals 2/3 the length of JN. Okay. All right, well, now it's just a little algebra 1 solving. 2/3 is multiplied by JN, so you can either divide by the fraction, which we don't want to divide by fractions, or we can multiply by the reciprocal of the fraction. So I'm going to multiply both sides of my equations, not by 2/3, no, heck no. We need to multiply by the reciprocal. The reciprocal is 3/2, so 3/2. Okay, so the 2's cancel and the 3's cancel, giving us just JN, or 1 JN. And then 3/2 times 22. If you want to go 3 times 22 and then divide it by 2, you can do that. I really like to cancel ahead of time, so I'll say 2 goes into 2 once, 2 goes into 22 11 times, 3 times 11 is 33 units. Okay. So I know the length of JN. Okay, so the next question we're asked is, what is QM? All right, so QM is this little guy right here. Well, I know that LQ is 2/3 of that whole median LM. Now, if this is 2/3, I know that this is 1/3. And what do we know about 2/3 versus 1/3? Well, 2/3 is double 1/3. So that means that 16 is double QM. Okay, or 16 equals 2 times QM, which means that QM is going to be 8 units. Okay, easy peasy. Great. Let's look at QP. QP is this guy right here. All right, so we are told that KP is 36, right? So we should know that QP is, okay, QP is what's left over after we hit the centroid. So QP is 1/3 of the entire median, 36. 1/3 times 36 is 12 units. Okay, let's move on. All right, compared to the first three questions, it's going to be lightweight, okay, or light work, however you guys want to say it. Okay, so in each figure below, on Alex, you can like drag, these segments so that you can move them this way and that way. Okay, same thing with this guy. You can move him this way and that way. What you want to see is if you can make a triangle. Right? Can you make a triangle with this? If you can make a triangle, then obviously the answer is yes. Okay, it says create the triangles if possible. So if you can make this point and this point meet right there, just go that way and go that way, so that you have a triangle with side lengths of 3 and 3 and 5. You're in good shape. That's all you need to do, just drag it over. Okay. Same thing with the 3, and the 7. Hopefully, when you drag this down, and you get the 3 here, and you drag this down, and you get the 3 here, you say, oh, wow, 3 and 3, you know, it'll never get to 7, so that's not a triangle, okay? So that's one of them that you would type in. There's no triangle possible because those two smaller sides, if you add them together, it's not bigger than the third side. Okay? That's going to be as easy as you can get. Now, from that little, you know, hands-on type of a question, you should be able to come up with the fact that if I want to know whether or not 3 numbers can be the sides of triangles, it's real simple. You take the sum of, you can say any 2. I always take the 2 smallest sides. Okay? Take the sum of the 2 smallest sides, okay? And that sum must be greater than the third side. If it's not a triangle. Okay? Just like before here, you had 3, 3, and 7, right? And you say, wow, 3 plus 3 is 6. Is 6 greater than 7? No. That's why when you have these two sides trying to connect, okay, they can't connect because 7's too big. Okay? This one here, 3 plus 3, 6 is greater than 5. Yes. So this was a triangle. Okay, so let's look. Now they gave us some decimals. Ooh, try to scare us with decimals. What's the point? Get it? No? Okay. Just take the 2 smallest sides. The 2 smallest sides here are 12.0 and 3.8. And your question is that greater than 14.9? Yup, it is. So because it is, you say they can be the 3 lengths of a triangle. Sure. Okay. Now this one. You got a 3, you got 11. Is that sum greater than 21? Nope, it's not. You got the 21 here, then you got the 3 here, 11 here. Can't be a triangle because this point and this point can't touch each other. Okay? All right, that's a big no. Okay. One last thing, it's got to be greater than, not greater than or equal to. let's say for a quick example, hopefully this will take away any chance of you all getting any of these questions wrong. Let's go back and just erase this a little bit here. Yeah, close enough. Just erase the whole thing. All right. Let's say that I had 10. And then I said, all right, I got one segment that's 3 long, and I got one segment that's 7. So 7, 3, and 10 is my question. Can that be a triangle? This is not a triangle. It's a thick line segment, but it's not a triangle. Okay? Why? Because if I take 3 plus 7 and I ask if it's greater than 10, the answer is still no. Okay? If I take a 10-inch, piece of string and I put another 10-inch piece of string on top of it, that's not a triangle. It's just a couple of strings smushed on top of each other. Okay? This must be greater than, not greater than or equal to. All right, I'm not going to talk about that anymore. All right, let's look at this next one. This next one should be simple because you did it in previous units. What do you know about the 3 angles of a triangle? Sum is 180. So, is the sum 180? So I have to ask, 21, 102, 57. Does that add up to 180? Yes. It's a triangle. 55, 65, 35. Well, that's 155. That's not 180. It's a no. Can't get it much easier than that. Okay. All right. So now we've got determine if given measurements define a unique triangle, more than one triangle, or no triangle. Okay. So the segment one is pretty straightforward. Okay. If I have 3 segments, let's say we have like 10, 20, and we have 13. Okay, 10 plus 13 is greater than 20. Boom, it's a triangle. Okay? And I know that there are no other sizes of sides that can give me 10, 13, and 20. Here's my question for you. What is the sum of these 3 angles? Well, you know it's 180. What if I doubled these? I doubled the 10 to 20, I doubled the 20 to 40, and I doubled the 13 to 26. Okay? What do those 3 angles add up to? 180. And believe it or not, they're the exact same measures. Those 2 are the same, these 2 are the same, these 2 are the same. Okay? You have 3 identical angles in both of those triangles, right? So with that in mind, let's do these 2 questions real fast. Okay, we got a 3, an 8, and a 4. Take the sum of the 2 smallers. Is it greater than 8? No. So no triangle possible. End of story. Let's say it was 3, 4, and 5. 3 plus 4 is greater than 5. You would simply say, yes, triangle is possible. And then the measurements, you would just say that the sides are 3, 4, and 5. That's it. Now angles, 40, 90, 50. 40 plus 90 plus 50. Does that equal 180? Yes, it does. Okay. But again, there is a triangle possible, but could there be more than one triangle with a 40, a 90, and a 50? Okay. I just showed you before that the angles don't give you the size of the sides, the SIZE of the SIDES. Let me give you one more quick example of that just to drive it home. Okay. If this is an equilateral triangle, okay, let's say this is 10 feet on each side. What are the angles? Well, equilateral triangle, 180 divided by 3. Each of these angles is 60 degrees, right? Let's draw a big equilateral triangle. Let's say each of these sides is 1,000 feet. All the sides are congruent. What are these angles? They're still 60, 60, and 60. So 60, 60, and 60. Is there only one size of a triangle that has 60, 60, and 60? Well, no. Here's a counterexample. Okay? If you have three angles of a triangle, then you can have triangles with measurements that have to be similar, but you have infinite equilateral triangles. You could have them with side lengths of 0.8 or 1,000,000.53 or 72 trillion each. Okay? So yes, the triangle is possible. Then you'll want to check out what Alex asked you as far as which sides or the size of them that the measurements are going to be going with. Okay, let's flip it here. Okay, now this one here, least to greatest. And here's what you need to know about this. Okay, the angle opposite a side in a triangle, as well as the side opposite the angle. Okay, the relationship is if one angle is bigger than another angle in a triangle, then the opposite side is going to be bigger. If one is smaller, the opposite is smaller. What do we mean by that? Let's look at this question. Right now, they've given us two angles. They've given us 54 and 45. So right now, I know that the side opposite this angle, so this opposite of the 54 is GI, okay? So angle H was opposite of GI. So angle H versus angle G, by the way, is opposite of what's that, HI. Okay, check it out. 54 is greater than 45. So I know that angle H has a larger measure than angle G. That means that GI has a larger measure than HI. Okay, so if an angle is larger than another angle, its opposite side is larger than the other angle's opposite side. Okay. So right now we know two angles. Let's find the third. Let's find angle I. Angle I is going to be 180 subtract 54 plus 45 is 99. So it's 81 degrees. Okay. So let's do this way. Let's do angles from least to greatest. The angles from lowest to highest, or least to greatest, is angle G, then angle H, and angle I. In order, lowest to highest. Okay. That means that opposite of angle G is going to be the smallest side, because G was the smallest angle. So that means HI will be the first side that I list. H is the middle angle. H is opposite segment GI, or IG. And then the largest angle I is opposite segment GH. Okay, so when it says order the side lengths from least to greatest, make sure that you give them the side lengths from the lowest to the highest. Okay, that's it. We got one more. Okay, this one's kind of fun. The Hinge Theorem. Hinge Theorem just says that if I've got two angles, okay, angles are made of two sides, right? So let's say I know the length of this side is 10, this side's 11. And on this other angle, it's also 10 and 11. Okay? What the Hinge theorem says is the following. If I know that this angle right here, let's say is 70 degrees, and this angle right here is like 85 degrees, then that means this side is longer than that side. That's about it. So if you have two sides of an angle that are congruent to the two sides of the other angle, then the angle between them tells you whether that third side of the triangle is going to be larger or smaller. Okay? Now, conversely, if we are given, instead of the angles, and if we're given that third side, let's say this is 14, okay, and this is 18. Okay, so if we are given this information, we say, oop, 10, 11, 10, 11. So we know something about the angle that are created by the 10, 11s. You look at the opposite side, the opposite side. Okay, because 18 is greater than 14, this angle, the starred angle, is going to have a greater measure than this angle, right? So if you have the two sides congruent in both angles, then bigger angle gives you bigger third side. Bigger third side gives you bigger angle. All right, so let's look at these two examples. All right, I see little congruent slashes here. That means that AB and CB are congruent. Okay. Now, we need a second angle side for each of them. Oh, look, BD. So we've got this angle here, which is made up of BD and then a side with one mark. This angle right here is also made up of BD and a side with one mark. Okay, so they both have one congruent slash and BD. So that means that both of these angles have side lengths that are congruent. The sides of the angles are congruent. But now, let's just look at the angles that are that are formed here. So this angle is 22, this angle is 39. So it asks me, what about AD versus CD? So is AD greater than, less than, or excuse me, less than, greater than, or equal to? Which is it? Well, since 39 is greater than 22, the 39 tells me that AD is greater than CD. Okay? You say, well, when can it not be determined? It cannot be determined if the two sides of the angle are not congruent. So let's say that, yeah, if for some reason this side over here, if BC were 8 and BA were 9, okay, you'd say, well, okay, you got BD and an 8, you got BD and a 9. Well, I can't compare those two angles. I can't compare the angles and the sides. Why can't I compare them? Because the side lengths have to be the same in the angles, right? These ones were, so we were able to say that AD is greater than CD. All right, and now finally, this question. Do we have two angles that have sides that are the same length? I see a 1 mark and I see a 2 mark. So yeah, we do. So we have angle F angle F, let's just trace it. And we're going to trace angle F. Okay. Angle F has side lengths that are congruent to angle Y. Okay. So now they want to know angle F versus angle Y. This angle versus this angle. Okay. The angles themselves are created by two sides that are congruent to the other two sides. So now all you can do is you can look at the opposite side and say angle Y is opposite of 17 and angle F is opposite of 19. Angle F's bigger. Okay. So if those markings had not indicated that those two angles were made of sides that were congruent, you would be able to say it cannot be determined. But this one can be determined. We're at the end of the line. Day 2 done. See ya.